So now we get into what we actually did in class. Here's a vector W, here's a vector V. I asked people to sketch that and sketch the projection, and people were drawing projection lines all over the place because they weren't coming down at a perpendicular. And it's confusing when you first see it. You got to learn to look at it, but you quickly get used to that. Okay? So I anticipated errors, and I actually got errors from people I shouldn't have been getting errors from, because they've done statics and multivariable calculus and all that. People who haven't, people who've just got the trig basis and haven't had a lot of these other courses, it's a challenging, mildly challenging task. You gotta get used to it. Okay, well anyhow, again, projecting the W to the V. Now there's a notation that we use that I didn't mention in these green diagrams. It's the projection onto V of the vector W. So it's the projection of W. Projection parentheses W means projection of W. The V down here is kind of a modification that tells you what vector we're projecting W onto. Okay? So that's the notation. And this is a vector. Now there's also the scalar projection. And the scalar projection is just the length of this vector, except that the scalar projection is negative if this vector is in the direction opposite the V vector that you're projecting onto. And I alluded to that here. Okay? Now the main idea here though was we project W onto V, we get this vector. We project V onto W and we get this vector. Okay? Projecting V onto W, very similar to the diagram I drew here. You got to go from the tip of V perpendicular to the line of W. And right there is our projection vector. Now, a little notation. This is the magnitude of this. Now, what's the difference between this expression and this expression inside the magnitude signs? Well, the difference is I've got an arrow over this. Okay? And actually, maybe I shouldn't even written this because this would be the scalar projection. Okay? So really I should probably have a plus or minus in front of this, but then I hadn't explained the plus or minus, except I kind of did, because if this vector is in the direction opposite the direction of V, as would be the case here, we'd have the negative, and here we'd have the plus. Then this would be what we call the scalar projection. So I might actually want to change what I wrote here. It's a little confusing. It's a confusion that would be hard to get out of, but maybe I want to say that this scalar projection is just the magnitude of W times cosine of theta. So maybe I'll replace this by so if this is gone and I replace it with this, this would be what I mean by the scalar projection. We'll clarify that. Right now, again, we're just getting used to drawing these things. We'll worry about the notation. But I think I kind of blundered a little bit with the notation there. Okay, now, what possible good is all of this? Okay, we've got some notation. Well, let's take a ball on an incline. And let's assume that the ball is going to move from here to here, so that our displacement vector is from here to here, although I drew it up a little higher. There's our displacement vector. Then we have our gravitational force vector. Now, some people are inexperienced at drawing force diagrams. Not everybody did this right away, but I think everybody understood it when we did it. The force diagram, we draw the weight vector, which is the vector representing the force exerted by gravity. Now, last time we saw that the force exerted by gravity is just the mass of whatever the object is multiplied by the acceleration of gravity. Newton's second law. in any case, within that context, we've got the ball in the incline and we've got the force vector. At any position of the incline, the force vector is straight down because that's the direction gravity pulls things in. Okay. Now we want to do a projection. Okay. We want to do projections involving these two vectors. So I say, well, let's sketch delta S and F gravitational from the same initial point, because that's what we do when we sketch the projection. It doesn't matter. Well, let's just take that. Okay. So we sketch them from the same initial point, and then I wanted you to sketch the projection of delta S onto F gravitational, the gravitational force. So we wanted to project this vector onto this one, and then I asked you to project the gravitational force vector onto delta S. Now it turns out that there's a lot of similarity between the results that we're going to get, but your choice of which vector to project on kind of influences the way you think, and it's going to turn out that for the purposes that we're doing, for which we're doing this, it doesn't really matter which one you choose. You get the same result, but the way you think through the result is a little different depending on which projection you do. So, yeah, that probably doesn't make any sense to you at all, so you can ignore it if it doesn't, but come back to the idea. So, here's the picture. Okay, here's our delta S vector, here's our F grav vector with the same initial point. That's what we do when we do projection, when we sketch a projection. So we project the F grav onto S. That's what this one says, the projection of delta S. Sorry, that's the second one. That's the projection of F grav onto delta S. So right there's the picture. We go from the tip of F grav to the line of delta S, and you know, delta S is long enough that the line of delta S, well, where the projection line meets the line of delta S is actually kind of within the vector delta S. That doesn't matter a bit, just as long as you know to extend the delta S vector if you need to. Okay, so we have this picture of the projection of this projection. So this projection goes right there. One thing that we know then is this angle. Okay, I say it's 60 degrees. How do I get 60 degrees out of this picture? No, gee, I don't know how I get 60 degrees because I never said anything about, oh yeah, I did. 30 degrees, right? So this angle here for the picture is supposed to be 30 degrees. So if delta S makes an angle of 30 degrees, what is the projection of delta S onto F grav? And this is the question we're answering with this picture. Well, if this angle is 30 degrees, then this makes an angle of 30 degrees with horizontal. It's 30 degrees below horizontal, and we'll say more about that later. But for right now, it's 30 degrees below horizontal, and this one is downward vertical, which means that from horizontal to vertical is 90 degrees, and we suck out 30 of them by going from here down to here, leaving 60 between here and here. So we have 60 degrees right there. Okay? So now, if we want to calculate the scalar projection, we can just take the length of the F grav vector and multiply it by the cosine of 60 degrees. It'll give us the length of this vector, and will also tell us that this vector is in the same direction as delta S. Even if we hadn't sketched it, it would tell us that. And the result would be consistent with our sketch. Okay? Now, the other thing we can do is we can project delta S onto F grav. Okay? And that's this picture up here, and it should be pretty self-explanatory. F grav is straight down, delta S is here, same initial point, tip of delta S, project back to F grav at a right angle. Looks like this. And we can see that this vector is going to be our projection. And I don't think I labeled that, and I don't see my orange chalk, so we'll just consider, you know, if you're drawing a picture of it, label it. Actually, I'll label it in green. This is our projection onto F graph of delta S. Now there's a terminology that I don't see on the board. I've written it out in the prelude to the assignment. The terminology is now the scalar projection, or the projection vector, is the vector component of this vector in the direction of this one. Okay? Now, you don't necessarily know what that means, but that's important terminology. So this is the component of F graph parallel to delta S, in the direction of delta S. Okay? This vector is the projection, is the component of delta S in the direction of F graph. And that notation's, or that terminology is going to become extremely important in our next class. Okay? Another way to put it is, another way we could put it is, this projection is the component of the gravitational force parallel to our displacement. And this projection is the component of our displacement parallel to F graph. Okay? So this component here is going to be F parallel. And this component here would be delta S parallel. Wherever your delta S and F vectors are. And now, I'm not going to prove this to you right now, because it can be proven, at least with certain assumptions. The assumption being that a vector is, the action of a vector is identical to the action of its two components, the sum of the actions of its two components. But again, we don't worry about that. If you know a lot about vectors, you understand what I just said. If not, you don't. Okay, the work done here by this force through this displacement is equal to the product of F parallel, the component of F parallel to delta S, this vector, and just the scalar projection, multiplied by delta S. And it's also equal to what you get if you multiply delta S parallel by F. In other words, this multiplied by this is the same as this multiplied by this. Now we'll see what good it is to think about components and so forth next time. We just want to get used to the idea of projections. Now the reason these are the same is your F parallel here would be your force times the cosine of this angle. And that's multiplied by delta S, right? Okay? And this is your force multiplied by your delta S parallel. Well, your delta S parallel is delta S multiplied by the cosine of 60 degrees to get this. Just look at this triangle. Well, this and this are identical. They don't look identical, but by the commutative law, and somebody was astute enough to say, well, that's a commutative law. Or is it the associative? Well, it's actually kind of a little bit of both. But the commutativity, we can reverse this multiplication, and if we do, we get this without changing the result by the commutative law. Now, implicitly, we're using the associative law, we're grouping this, and we're grouping this, but we don't need that grouping. Okay, so the equality of this expression and this expression, which comes directly, these expressions come directly from these triangles. The equality of these expressions mean that you could calculate the work either way.